In this video, we will get an understanding of what is meant by the term data structure. Recall that up to now, we have mainly been working with three data types. They are numbers, strings, and booleans. These are all called primitive data types. We have also come across a couple of special data types, called null and undefined. Now we will look at complex data types. A complex data type is a data structure that is built into the programming language. You use data structures to store other data. Complex data types are also sometimes called composite or compound data types. You can think of a data structure as a pile of boxes with labels. You can create a variable and make its value be equal to the whole pile of boxes. When you want to retrieve some data in your data structure, you first use the variable name to get the pile of boxes. Then you look at the labels on the boxes, and retrieve the piece of data in one of the boxes. You already used the list data structure. But lists are not the only sort of data structure. There are many other types of data structure. General-purpose data structures are flexible and can be used in many different ways. There are also certain data structures that are more problem-specific, but we will not go into those here. Two very common general-purpose data structures are lists and dictionaries. These data structures can be found in many programming languages. And they are also the two main data structure available in Möbius Modeller. Let's look at these two in more detail. We will not be using dictionaries straight away, but it will still be useful to have a basic understanding of how they work now. You can think of the list as boxes organized in a strict sequential order. The labels on the boxes are integer numbers, starting at 0. These labels are generated automatically and cannot be modified. The labels are called indexes. Here is a more abstract diagram of the list. A list consists of a sequence of data values. Each data value can be accessed using an index. Indexes can be positive or negative integers. An important property of the list data structure is that the items in the list are ordered. The order is defined by the index values. The 0 index is the first item. The 1 index is the second item. And so forth. Here are some examples of lists. We already covered many of the basics of lists. Lists can also be nested inside one another. So lists can contain other lists. The nesting can do to any depth. So you can have lists of lists of lists, and so on. You can also create lists that contain a mix of complex and primitive data types. The list is a very flexible data structure. To access values in a list, you use square bracket notation, with the index in the bracket. When lists are nested, you can create a chain of square brackets indexes. Try to see if you can follow the two examples in this slide. You can think of dictionaries as a set of boxes with unique labels. The boxes are not placed in any particular order, but each box has a unique label defined by you. The labels are called keys. Here is a more abstract representation of the dictionary. A dictionary consists of an unordered set of data values. Each data value can be accessed using a key. You can use any kind of label for a key. An important property of the dictionary data structure is that the items are not ordered. Instead, you use the keys to access items. The keys have no specific order either, but the keys must all be unique. Here are some examples of dictionaries. The dictionary is defined using curly braces. Each data item in the dictionary has a key and a value, separated by a colon. Just like lists, dictionaries can contain different types of data. Dictionaries can also be nested inside each other. So dictionaries can contain other dictionaries. The nesting can do to any depth. To access values in a dictionary, you use square bracket notation, with the key in the bracket. When dictionaries are nested, you can create a chain of square brackets with keys. Try to see if you can follow the two examples in this slide. We can also nest lists and dictionaries inside one another. In this example, we have created a list that contains 3 dictionaries. And in this example, we have done the opposite. We have created a dictionary that contains 3 lists. Notice that the actual data that is stored is the same as in the previous slide. The way that you structure your data is flexible. There are usually many ways to achieve the same thing. The final example has 3 levels of nesting. We have a list that contains 3 dictionaries. And each dictionary contains 1 list. Finally, before we move on, let's touch on one more important concept related to data types. When you call a function, you will often need to pass data to that function via the arguments. When passing data, primitive data types and complex data types behave differently. This can be a little confusing at first. So let's dig a little deeper. First, we need to understand that data stored in memory has an address. The table shown in the slide is a simplification, but the main point is that each piece of data has a unique address. Note that when coding, you never actually see the address. It is something that the system will take care of for you. Now let's look at 2 specific behaviors that differ for primitive and complex data types. They are the assignment operator and passing variables. Let's look at these 2 examples. With the primitive data type, setting one variable to be equal to another variable copies the data. This means that the data will be duplicated in memory. With the complex data type, setting one variable to be equal to another variable copies the address. This means that the data will not be duplicated in memory. Only the address will be duplicated. In the example, we can see that A1 and A2 have separate values, but B1 and B2 have the same value. Continuing with the same example. If we now change the value of the A2 variable, it will not affect A1. However, if we change one of the items in the B2 list, then B1 will also be affected. Let's look at the second behavior where primitive and complex data types differ. This happens when passing variable to functions. For primitive data types, the data is copied and passed to the function for processing. This is called passing by value. For complex data types, the address is copied and passed to the function for processing. This is called passing by reference. For the primitive data type, the changes that the function makes cannot affect the original data store in the A1 variable. This is because the data is passed into the function by value. For the complex data type, the changes that the function makes can affect the original data store in the B1 variable. This is because the data is passed into the function by reference. In the example, a list.add function is called. This function has 2 arguments. The first argument is a list, so it is a complex data type that is passed in by reference. The second argument is the value 7, so it is a primitive data type that is passed in by reference.